Hi folks, in this lesson we're going to be looking at motion in an electric field. Now there's going to be three things that we're going to do with this. So the first thing is we're going to look at charges where they're moving parallel to the electric field in a uniform field. The second thing, we're going to look at charges moving parallel to the field in a radial field. And finally, we're going to look at charges moving perpendicular to a uniform field. So there's three things in three different cases that we're going to look at. For our first case, we're going to look at charges moving parallel to a uniform electric field. And most of this we've already covered in higher, so that this is probably more of a revision than something that's brand new. And so just to remind you, what we had is we had two parallel plates, and these two parallel plates, if we put a positive charge on one side, a negative charge on the other side, then you're going to have an electric field, and your electric field would look something like this. I won't do too many lines, just there. And if we're going to move the charge parallel to this, so we would start with a small charge, and we're going to call this Q. It's not very good Q. And this is going to be a positive charge. So with the charge here, it's just, if it's held here, or if it's sitting here, it's not going to do very much. It's right against the negative plate. But if we want to move it over to say here, then we're going to have to apply a force to do that, and we're going to have to do work on it. And so we would say, let's see, to move the charge, work needs to be done. Okay, and from higher we had the formula EW is equal to QV. Now it will be written in higher and in advanced higher, it would be written as big QV, but just for the sake of this, I'm going to just start writing it as QV. Same thing, you will not be penalised for using a small q as opposed to a big Q. It doesn't make any difference. But what I really want to do is to differentiate that this is the charge that's placed in the electric field. And with a uniform field, it doesn't really matter. But when you'll see when we start looking at radial fields, then the radial fields, you'll have a charge that creates the point charge, which we'll call big Q. And the charge that's in that field created by the point charge will be little q. And so I just want to differentiate the two of them, but they're both the same thing. Now, as you force the charge there, you're going to apply a force to move it against the field. And so that's going to require a force to move it. And the distance that you move it through, force times distance, will be equivalent to energy as well. You'll remember when we derived the terms for the electric field strength, then we used that principle of work done is equal to QV, which is also equal to force times distance. Now, so as you apply force to it, you're going to move the charge across the electric field parallel to this, and the charge will gain potential energy. So the charge will gain EP. By the time you get the charge over to here, you'll need to hold it there. You'll need to apply this constant force to keep moving it across. And as when you release the charge, then the charge is going to accelerate back this way. And so we're going to have an acceleration, and that's going to be proportional to the size of the force that you had to push it across. It's going to be accelerating with the same force back. But as it's accelerating, the charge is going to gain Ek. So we can say when released, charge gains Ek. Now as it gains Ek, it's going to lose this potential energy to the point where it will be at its maximum Ek at this point here, when the gained potential energy will be 0. And so we can equate the two of them, and we could say that the EW is going to equal to the EP gained which is going to equal then the Ek gained. And this would be the Ek gained at positive side and the Ek gained at negative side. Okay, so taking these, and the formula that we have would be QV is equal to half mv squared. Okay, and you can rearrange that for whatever you require of your purposes to be. Now the force that we use to apply it, I'm going to put this sort of more in passing because this has sort of been done already. So the force is charge times electric field strength. Electric field strength can be determined by the voltage over the distance. So the distance here would be the plate separation. So we would have distance here, and we would have the voltage across that as well. Putting this all together, we would have force is equal to QV over D, which then takes us fully back round to force times distance for the work done in the QV. Okay. All right. Now, we'll do a couple of examples here. The first example would be really a direct copy from what you would have done at higher, if you remember, in the particles and waves. So we would have, let's just do a quick sketch out of something here. We'll have an electron gun. And we're going to have our anode here, cathode, V equals 1.5 kilovolts. So the electron is accelerated through a potential difference of 1.5 kilovolts, and we would want to find the velocity. So really straightforward. We're just going to say work done is equal to Ek gain. It's not particularly well focused, is it? That's better. So work done, charge. Now this is the charge of an electron, the voltage between the two, the anode and the cathode. And we're going to have kinetic energy, half mv squared. Do not confuse the v and the v. This is voltage here. This would be the velocity of the electron. So this is actually what we're trying to calculate here. And if we rearrange for v, then we can have v is equal. So that would give us 2 times QV, because the half comes over here, becomes a 2 over m, and the square root of 2QV over m. Then we can just sub in our values. So 2 times charge of an electron, you can go and look it up in the data sheet if you need to, 1.6 times 10 to the minus 19 coulombs, times our voltage, which is 1.5 kilovolts, so that's 1500, and the mass of an electron, again, you should go and look this up in the data sheet if you need to, so that would be 9.11 times 10 to the minus 31 and the square root of all of that. And so that works out to be 2.295, so let's call that 2.3 times 10 to the 7. Meters per second. Now obviously you're going to watch that your answers are not going to be greater than 10% of c. If they have a velocity that's greater than 10% of c, then we get into the relativistic effects which need to be taken into consideration. So you generally won't be given an example that has you will be given an example that has a velocity greater than that. So if you are getting a velocity greater than that, one of the most common mistakes is you forget to take the square root of your answer, and then you're going to get an answer that's much bigger than the speed of light. So moving on, we can have a second example. So really simple. If we have a 2 kilovolts, and then let's see, there's a you can't see any of this. 2 kilovolts, and let's just say that it's an alpha particle. How much work would need to be done to put this alpha particle up to here? So alpha particle, 2 protons, has a charge of +2 in terms of unit charges, and so that would be 3.2 times 10 to the minus 19 coulombs. How much work done? So work done to move charge to the opposite plate, simply EW is equal to QV. We would have 3.2 times 10 to the 19 times 2,000, and that'll be 6.4 times 10 to the minus 16 joules. Now we'll look at charges moving in a radial field. So a radial field will be created by a point charge. So if we have our point charge here, then our radial field will be something just quickly sketched out. Like so, and we'll call this field has a magnitude of charge Q. So what do we know about this this field as we have? Well, force, Coulomb force. The Coulomb force would require another charged particle to be in there. So let's stick. Again, my Q's are rubbish. Sorry. It looks a bit like a deranged day. But this is Q. So positive Q charge, and we have our positive charge that's setting up the field. And so the force of that, the Coulomb force, would be Q times Q over 4 pi epsilon naught r squared. We would also, if we ignore this charge altogether, then because this has charge, there would be an electric field around it. So E is equal, then that's just Q 4 pi epsilon naught r squared. And finally, the electrical potential around this, you would have V is equal to Q 4 pi epsilon naught R. So this would be measured in newtons. This is newtons per coulomb, and this would be in volts. Also, you could have volts per meter. Okay, so now what are you doing? Well, you have your charge Q at this point in the field, and what we would define the electrical potential as is the amount of energy per coulomb to bring the charge from infinity to a point at r meters away from the charged object. So we're going to have our radius here, which is going to be the distance between here and here. So as you're bringing this charge from here into here, you're doing work on it, and so work is done to move it closer to charge Q. Okay, so you're doing work on charge on little q to bring it closer to big Q, and the closer you get to big Q, the more work that you need to do. And so the work that you're doing, work done, is going to be EW, and we'll say, so work done and move it closer to charge Q, charge Q gains EP. Okay, so as you move it there, you're going to be doing work on it, but it's all the time is gaining EQ. So if we bring it to a point r meters away from big Q in the field and just hold it there, then it will have gained potential energy. Now the work that you've done will be equal to EW, which is QV. That's a better Q. So QV. But V, whereas before it's the same as the uniform field, V was just the voltage or the potential difference between the plates. But in this case, we have our electrical potential. Just incidentally, while I say that you're never going to have a case in advanced higher where you're not moving the charge parallel to the field. You're not going to have a charge that's moving across around here because the maths would be too difficult. You would start to get a sort of orbital type thing going on here, which we're just not going to look at. So the work done, EW is equal to QV. V is electrical potential, which is here, and so if we just substitute that in there, we're going to get the amount of work done is going to be little q times big Q all over 4 pi epsilon naught r. Okay, so be careful, that's almost exactly the same as this, as the force, but all we've got is we've got an extra distance in there. So now, if we take this charge and if we were to release this charge, then it's going to start to accelerate. It's going to be experiencing a force. So we'll release it. There'll be a force. There'll be an acceleration. And there'll be an increase in kinetic energy. So the maximum amount of kinetic energy that it could gain would be equivalent to the amount of work that you did to bring it to that point. And so we can see EK max is equal to work done. And so we would then have Q over big Q 4 pi epsilon naught r is equal to half mv squared. Now from this point on you can rearrange and you can find out whatever it is you need. We'll go through a couple of examples to show how we would use this in an actual question. So example 1, calculate the energy required to bring a 3 nanocoulomb charge to within 20 millimeters of a 6 microcoulomb charge. So we're bringing it from a very large distance or infinity, and we're bringing it all the way up to within 20 millimeters of this charge here. So you're going to do work, so work done EW is equal to QV, and be careful with your Q's, so this is small q, which is this, and V is the electrical potential at 20 millimeters from this charge here. So that's going to be Q times big Q (4 pi epsilon naught r), and so we can have 3 times 10 to the minus 9 times 6 times 10 to the minus 6 over 4 pi times 8.85 times 10 to the minus 12 times 20 millimeters. Okay. So that would give us 8.1 times 10 to the minus 3 joules. Okay. Now we'll look at a second example, and this is this kind of example. I've seen these asked in exam questions before, and it's fairly challenging. There's a separate bit in the notes about this. It's when we're looking at Rutherford scattering. Now, if you remember Rutherford's scattering experiment, he fired alpha particles at a gold leaf, and he came up with three postulates from that. The first one was that most of the alpha particles went straight through, and they struck a screen at the back. It was a scintillation screen, a scintillation counter. So as the alpha particles struck the screen at the back, it would give a flash of light. So as they're firing the alpha particles through, they notice that most of the alpha particles go straight through. Some of the alpha particles are deflected, and then occasionally they would have an alpha particle that was rebounded. So as it rebounded, from this they came up with the theory that it was making a head-on collision with the gold nucleus. But if we think about this, and if we actually think about the physics involved in this, and so if we have our gold nucleus here, so Au, and we have our alpha particle there. Now, as our alpha particle is flying in, the electrical potential, I guess the electrical potential energy, so this is what we've been talking about. If we have V, which is our electrical potential, so we'd have Q over 4 pi epsilon naught R. As this gets closer, R gets smaller. Now, if we're talking about this is electrical potential, so the electrical potential energy, all you're doing is you're just adding in the charge of this here. But as you get closer and closer and closer, R gets smaller and smaller and smaller. So the amount of electrical potential energy, and this is kind of happening in reverse, it starts off over here far away with an initial EK. Now, as it's moving in, it's doing work against the field, and the amount of EK is going to decrease because there's going to be a force pushing it backwards, and so the amount of EK decreases until it gets to zero. Depending on its initial kinetic energy will depend on how close it actually gets to the gold nucleus, but it will never, in the truest sense of the word, make a head-on collision. It just will not get anywhere close there. If it were to make a head-on collision, and where we actually have it striking the gold nucleus, then at that point R would be zero. If R is zero, then you're going to need an infinite amount of initial EK, which you can't have. So the question would typically be is you would be given an initial velocity of the alpha particle, and you would be asked to find the distance of closest approach. And so this is the closest approach. To find the distance of closest approach. So find the distance of closest approach for an alpha particle fired at a gold nucleus. Okay, so let's make a little sketch of this. So we have our alpha particle here. Typically what they did with these is that you would have an alpha generating source in a lead lined box that was sort of open at one end, so that anything that was fired out all in this direction would be absorbed, would not be able to penetrate through, but it would have an aperture that was open that would be able to send out this beam of alpha particles. And so as these alpha particles left, they had kinetic energy. Now, the velocity that an alpha particle is emitted is typically around about 0.1 c. And so we will have, let's call that, so V of alpha is going to equal, so let's call it 3 times 10 to the power of 7 meters per second. So this is going to travel here until it reaches a point where the work done against the gold's electric field will equal the amount of initial kinetic energy it had. So we're going to do two things. We're going to figure out the kinetic energy that the alpha particle starts with, and we're going to figure out at what point in the field I, at what distance from the gold nucleus that would equal the amount of work done, which is over here. So what do we need? This is the gold foil. So we need to know the charge of an alpha particle. So well, an alpha particle is 2 protons, 2 neutrons, and so the charge, and I'm going to do Q of alpha is equal to 2 times 1.6 times 10 to the minus 19, and that's going to be 3.2 times 10 to the minus 19 coulombs. And we're going to need our charge of our gold nucleus, so gold Q AU, and there is 79. Don't ask me the atomic mass of gold, but I know that gold has 79 protons, and so there would be 79 times 1.6 times 10 to the minus 19. So we'll have 79 times 1. That's going to be 1.264 times 10 to the minus 17. Okay. Now, so we'll have our initial EK of the alpha particle is going to equal the work done against the electric field. And this is going to give us half mv squared, which is equal to qv. I'll just write this out in full, which is going to be qv over 4 pi epsilon naught r. We'll have half mv squared. Now we're going to find what we're looking for actually is we're looking for the distance of closest approach. So we're looking for this r. Rearrange this for r. Well, we can get rid of the half by moving it to 2 here, and then bring the r up here and bring the mv squared down there. So we would have r is equal to 2qv. No, this is wrong, sorry. 2, this is big Q there, so big Q here, charge of gold. So charge of alpha, charge of gold, yeah, there. So 2 Q times Q over 4 pi epsilon naught mv squared. Okay. Now sub in the numbers. So 2 times charge of gold, charge of alpha, 3.2 times 10 to the minus 19, times charge of gold, 1.264 times 10 to the minus 17. 4 pi times 8.85 times 10 to the minus 12 times, I have no idea what the mass of an alpha particle is, which I should have thought of before. So mass of alpha particle, well, it has 2 protons and 2 neutrons, so you go away and look at the data sheet and you would add up 2 times mass of a proton plus 2 times mass of a neutron, and with the magic of television it is 6.696 times 10 to the minus 27 kilograms. Okay, just like that, simple. So I feel like I'm going to do some TikTok video where I click my fingers and suddenly change the formula. Sorry, I'll shut up. Okay, and well, let's just click our fingers. Just like that. So 1.21 times 10 to the minus 14. And that would be meters. And so what that would mean is that the alpha particle would travel and it would get to a distance of 1.21 times 10 to the minus 14 meters away from the gold nucleus before it lost all of its kinetic energy. At that point it would briefly stop before rebounding and accelerating away. So now we're going to look at what happens when you have a particle entering an electric field at right angles to the direction of the field, or motion perpendicular to an electric field. In the two previous cases, the force has been in direct opposition to the electric field. So you could have in the case of two positive charges, you would have a repulsion, so you would have it acting in opposition. So, but you could also have the attraction, which would work in exactly the same way. But if we have our electric field like so, and I'll just draw again just a few field lines. Now, if the electric field is going this way, it must mean that we have positive charge and a negative charge here. If we were to draw this just like super accurately, then our field lines would kind of bow out from the edges, and as soon as if the particle was entering from, say, over here, then as soon as it sort of came into the region of the electric field as it bowed out, it would start to experience a force. But generally what we'll do, we'll ignore that and we'll assume that it sort of has a hard border just as it enters the field. So your particle is fired with an initial velocity. And so we'll have that initial velocity v, like so. And as soon as it enters the field, so at this point here, it's going to experience a force. Now, it's a positively charged particle, so at this point it's going to be experiencing a force going down. In the electric field, earlier we defined electric field as newtons per coulomb, and so we can just take that around a wee bit. And again, I'm going to use small q just because it's referring to the small q of this particle, but F is equal to QE. We also defined electric field strength in terms of potential difference. We defined it as E is V over D. And so now we have a situation where if we know the potential difference between these two plates, and we know the plate separation, we can determine the electric field strength. Let's call it D. So if we know V, we know D, and we know the size of the charge that's entering it, then we can determine the force. So substitute this into here. F is equal to Q, nice silly Q's again, QV over D. Now this particle, when it enters the electric field, it's going to experience a downwards force, and so it's going to start to accelerate in the direction of that force, and then that acceleration will obey Newton's second law. So F equals ma, which then is also going to equal what we've just derived as the force that the electric field is going to apply to it. And so that's going to be QV over D. Rearranging this for A, we'll get A is equal to QV over MD. So as it enters into this region here, it's going to start to experience a force downwards, it's going to accelerate downwards, but moving perpendicular to the field, there's no forces acting on it. And so at any point when it's in the field, well, it's going to, as it moves in, that there it has its velocity, and I'm going to call this VH. So its horizontal velocity, there's no forces acting perpendicular to the field. It has its initial velocity, but there's no forces acting on it, and therefore it's not going to accelerate horizontally. And so we're going to have a constant horizontal motion, and we're going to have a constant force being applied to it. And so this is exactly the same as projectile motion. Constant horizontal velocity, constant downwards acceleration, or could be upwards acceleration. The acceleration can be found by that, but it will just be a projectile problem from this point onwards that you'll find. So constant horizontal velocity, constant acceleration. Now, if you remember back to particles and waves in higher, and we were looking at electromagnetic forces and gravitational forces. The gravitational forces are many, many orders of magnitude smaller than electrical forces or electromagnetic forces. And so with all of these, we can ignore the effects of gravity. It will be almost minuscule in comparison to the force that this is going to experience due to the electric field. So we have absolutely no problem in, if we were to have this as a negative charge, we would have absolutely no problem in doing exactly this, but have it move in an upwards path like so. There's no problem with that. So as it enters the electric field, it's going to have constant horizontal velocity, constant downwards acceleration, and we're going to have this sort of projectile path. It's going to curve down and it's going to hit, and the point at which it strikes will depend on the initial horizontal velocity. Obviously, also the plate separation. If you have a bigger separation of a plate, if you fired it in up here as opposed to firing it in down here, but if you have a bigger horizontal velocity, and so if we gave it a larger horizontal velocity, it could come like this, or in extreme circumstances, you could give it a very large horizontal velocity, which would let it do this. Now at the point in this scenario, at the point at which it leaves the magnetic field, sorry, the electric field, so that point has left the electric field, and as soon as it leaves the electric field, again we ignore this sort of bowing of the thing, then it would continue in a straight path. So whatever its components of velocity would be, at this point you would have a vertical component of velocity, you would have a horizontal component of velocity, and that would determine its velocity there, and it would just keep traveling in a straight line. And then you could watch it. There's a number of questions that I think, certainly in RGC problem book, where it deals with this scenario, and I will get you to do it. But it's a tricky question. It will ask you to find out where on a screen it strikes, and so you've got a lot of steps. You've got to work out acceleration, You've got to do your projectile problem to see what its velocity is by the time it leaves here. I'll go through some of the basics with you here, and then and I might do another video just showing you how that's all worked out, because it is fairly in depth. Okay, right. So constant horizontal velocity, constant acceleration. So we're going to say for vertical, use your old friend Suvat. Right, let's have a look at an example. So what we've got is parallel plates. There's a potential difference of 1.2 kilovolts across those plates. The separation is 50 millimeters, and the length of the plates is 10 centimeters. And so what we'll do is we will directly in the middle of the plates, we will fire in a proton, and we'll fire in a proton at 6 times 10 to the power of 5 meters per second. And we'll see what happens. So, potential difference of 1.2 kilovolts, separation of 5 centimeters or 50 millimeters, and from the previously derived equation, we could have A is equal to QV over MD. Q, charge over proton, 1.6 times 10 to the minus 19. Hopefully I said proton there. Just do that. So there's a proton entering 6 times 10 to the power 5, and we know everything that we can have. It's going to be fine. Times mass, so 1.673 times 10 to the power of minus 27, I hope, I think, I remember. I could probably check it out, but I won't. You'll tell me if I'm wrong anyway, but it won't matter because I've already recorded this and there's nothing I can do about it. So anyway, I am waffling on. Again, the amazing power of TV has given me this, and we get 2.295, so 2.3 times 10 to the power of 12. That's a huge acceleration, 2.3 times 10 to the power of 12 meters per second squared. But what you've got to remember is that although that's a phenomenal acceleration, the particle is moving at 600,000 meters per second, and to the time that it's going to take to cover 10 centimeters is going to be minuscule as well. And so this acceleration is not going to be that dramatic, I guess, given the level of time that it's going to be moving through there. So once we have our acceleration, we're going to use this, and what we want to do is we want to find out at the point at which it strikes in here. I probably should have said that. Find out where. Find out where proton strikes. Okay, so in order to do this, if this is 50 millimeters, and I previously said that we fire it directly in the middle, then we're going to have 25 millimeters, no, has meters, 25 millimeters from the bottom. Again, plus minus. Right, so it has 25 millimeters to travel. It's going to accelerate that. Now, as it enters, remember, its initial vertical velocity is going to be 0. It's all horizontal velocity here, and then, but as it enters there, it's going to start increasing its velocity, but its initial velocity will be 0. So we're going to do suvat, and what we want to do is find time. So time there, and we're going to have 0.025. That's going to be 0. We don't really care about velocity at this point, and we have 2.3 times 10 to the power of 12. S equals ut plus half at squared times 2.3 times 10 to the power of 12, and that is times t squared. So t will then equal 1.47, let's call it 1.5 times 10 to the minus 7. Seconds. So really, really tiny time. And now finally, so it's going to be here, it's going to be traveling for 1.5 times 10 to the 7. Now what we want to know is it's going to cover 25 millimeters in that time. And where it is going to be horizontally after traveling for 1.5 times 10 to the minus 7, so 0.15 microseconds. And simply, we're just going to use speed distance time. And so we can find horizontal find our horizontal distance. And so d is equal to vht. So we'll have 6 times 10 to the power of 5 times 1.5 minus 7. And that gives me 0.09. So that would be 0.09 meters, which is going to be 9 centimeters. So it will travel a distance of, horizontally, it will travel a distance of 9 centimeters. So, which means it's going to strike somewhere around about here. Its full path would look something like, well, it's going to, so something like this, and it'll eventually strike 1 centimeter from the end of the plates. So that's one worked example. There's a number of different things you could do. I think I mentioned earlier that you could have a case where if this had been traveling slightly quicker, so say if this was 9 times 10 to the power of 6, then we would have had 90 centimeters it would have come. So by the time that it took to go through the plates, it would have only have traveled down to about here, and at the point at where it leaves here, it stops accelerating in every direction. It never was accelerating horizontally, but it would then just have constant horizontal and vertical components. There's a really good example in the RGC notes, which I think I'll probably just do a separate video for. I'll make that video and I'll post it up after this one, because it is quite complicated. There's another few extra steps, and you have to start messing around with geometry and things like that. But there are your 3 examples of motion in an electric field. Any questions, just ask, and we'll talk about this you have any problems in due course. But okay, well, thanks for watching, and I hope you have enjoyed it, stroke, if not enjoyed it, understood it. Okay, thanks then. Bye-bye.